Hello and welcome to this section of the Chemistry Tutor. In this section we're going to cover the topic of limiting reactants in a chemical reaction. It has a complicated sounding name because, reactants, what does that mean? Limiting, what does that mean? But I promise you, everything that we're going to do in this section, you actually already know how to do. I just need to kind of coax you into realizing that a little bit. And that's what you're going to find out, to be honest with you, almost all the way through the rest of Chemistry 1, is basically I've given you the tools already to understand how to do all the calculations. You know how to do the unit conversion technique I've been showing you over and over again. You know how to calculate molar mass, off the periodic table. You know how to basically deal with chemical reactions. The rest of all the topics, to be honest with you, are mostly applications of sort of special cases and things to think about, but we're not going to be learning new calculations or new formulas or anything like that. We're mainly going to be using what we know and applying it to certain cases. So from here on out, keep that in mind. It looks like we've got a lot of different topics coming down the road, but in reality, there's really not too many different topics. We're just kind of breaking up everything into special cases. This is a great example of that. Let me go ahead and explain what limiting reactants is for you in just a few sentences, and I think you'll realize that it's something you already knew but didn't maybe realize it. So it's a great example of what I'm talking about. In all the chemical reactions that we've been talking about, and I'll draw one on the board here in a minute, you have things combining on the left-hand side of the arrow, and they're combining to make the products on the right-hand side. The products are the things created on the right-hand side of the arrow, right? That makes sense. The reactants, that's everything on the other side of the arrow, of the equation. So the reactants are everything that you put into the reaction chamber. So when we say limiting reactants, we're talking about the things that are on the left-hand side of the arrow, the things we're mixing together to make our chemical reaction happen. Now the limiting part I need to explain to you, but that's sort of where we're going. Let me write one very simple chemical reaction on the board, and I'll be able to tell you quickly what a limiting reactant is. So remember the reaction, H2, 2H2 actually, plus O2 yields 2H2O. I picked this because it's very simple and it's something, that we obviously need because it produces water. So if you look, this is balanced. Four hydrogens, 2 oxygens, 2 oxygens. So this is balanced, right? What it basically says is if we take hydrogen gas and mix it with oxygen gas, which by the way we do in rocket engines, and if you react it, then it produces water. And also it produces a lot of heat because it produces an explosion. That's what's sort of left out of this reaction. We haven't talked about heat at all. We'll get to that later in chemistry class. But there's basically heat produced, but there's also a lot of water produced. So if you look at most rockets, a lot of them all of them that use hydrogen as fuel, you'll see a giant white cloud coming out of the end right after the fire. Well, that's water vapor. That's all that's being produced. It's just water vapor coming right out of the end. So this is a balanced chemical reaction. This is the products, obviously. These are the reactants on the left-hand side. Now, and here's the crux of this section here. We know from this reaction that if we take 2 moles of this hydrogen gas out of a bottle, right, it's delivered to your lab, and we mix it with exactly 1 mole of oxygen, because of the coefficients here, if we take 2 moles of this and 1 mole of this and we react it completely, we should expect to get 2 moles of water, usually in a gas state because of the heat involved. It's going to be a gas, but it's going to be water. So if we could somehow measure everything exactly, if we mix 2 moles plus 1 mole, it will yield exactly 2 moles of product, right? So this reaction was mixed in the perfect proportion. We measured exactly the right amount so that every molecule of hydrogen was reacted with every molecule of oxygen, and the reaction was perfectly consumed because we mixed everything perfectly. We didn't give too much of something or not enough of the other guy. So let me do a little thought experiment with you to point out the idea of limiting reactant. What if we don't mix these guys in the perfect proportion, the exact right amount? Because don't forget, they're mixing in the ratio of 2 hydrogen atoms to 1 oxygen atom. So that's why everything's locked in here. That's why this ratio really works out, because of the fact that the way the molecule's actually forming. In fact, let's say we have a giant sphere in our laboratory, a huge thing, and it's full of oxygen, way more oxygen than's actually needed to react with this little bit of hydrogen we put in there. We put a little bit of hydrogen in there, and then we put a match or something in there to ignite it, to cause it to react with the oxygen. And then what's going to happen in that case? What's going to happen if we have a little bit of hydrogen with a whole bunch of oxygen? What's going to happen? Well, what's going to happen is all of these hydrogen atoms are going to react. They're all going to be bound up with the available oxygen. They're all going to form water, right? All of this little bitty amount of hydrogen we have is going to form water. But we're going to have a lot of oxygen left in the chamber because we didn't put much hydrogen in there to begin with, right? So in that case, when we have just a little bit of one reactant and a whole bunch of another, and they're not perfectly in this perfect ratio all automatically ahead of time, one of these guys is going to be a limiting reactant. And in this case, the hydrogen is going to be a limiting reactant. And that's the title of this section, so make sure you understand it. If we flood the chamber with oxygen and put just a little bit of hydrogen in there, this is going to be the limiting reactant. The reason is because the reaction is going to proceed until one of these things is used up, and then it can't proceed anymore because you can't produce any more water if you run out of one of your ingredients. It's like making cupcakes. If you only have a few eggs, right? You have a lot of a lot of powder in your pantry, and there's a few eggs. Well, you're going to be limited in how many cupcakes you can actually make based on which ingredient you have the least of, basically. All right. So when you run out of eggs, if you have just a few eggs, you're done. You can't make any more cupcakes. It's the same thing. Once you run out of hydrogen, you can't make any more water. And that's why it's the limiting reactant, right? So if we flood the chamber with excess oxygen, that's what's going to be what happens. Now, if we flip the situation and we say, all right, well, let's do it differently. Let's create a reaction vessel and let's flood the chamber with hydrogen gas. We get a giant tank outside and we hook it up to our reaction vessel and we flood it with a ton of hydrogen. And we put just a little bit of oxygen in there, just a little bit, right? It doesn't matter how much. We're doing a thought experiment here, right? Then we cause that reaction to occur. Same thing's going to happen. The oxygen is going to begin combining with the hydrogen, producing water, producing water, producing water, until one of these things runs out. But if we have a whole bunch of hydrogen and just a little bit of oxygen, then we're going to eventually run out of oxygen much, much sooner, right? So when we run out of the oxygen, we're going to form all the water we're going to get, and we're going to say this is the limiting reactant. The oxygen in that case is a limiting reactant because it's what we had the fewest of, the fewest molecules, the fewest atoms. Once the reaction combines, once you run out of the oxygen, you're done in that case. So that, ladies and gentlemen, without any math, is what a limiting reactant is. In real life, if you're trying to mix these things in the exact right proportion, if you got it perfect, then really neither one is a limiting reactant if you did 2 moles of this and 1 mole of this, because every single atom and molecule was used. But in real life, you can never get it perfect. In real life, you can never measure exactly 2 moles of hydrogen. In real life, you can never measure exactly 1 mole of oxygen gas, right? So one of those things is going to kind of stop the reaction first because you're going to run out of it first. That one that you run out of first, right, is going to be what we call the limiting reactant, or the limiting reagent, depending on your book's definition. A reactant, reagent, basically they both mean whatever's on the left-hand side of the arrow. So we have covered, in theory anyway, what this is all about. What I'd like to do is work a real problem to show you how to do that. So let me go ahead and write a real reaction on the board. Let's look at 2 times lithium, 2 moles of lithium hydroxide plus carbon dioxide is Li2CO3, which is lithium carbonate, plus H2O. So this is a reaction, and for those of you who are curious, basically this is called lithium hydroxide, this is carbon dioxide. When you put them together, you get some results over here on the right-hand side. Actually, we use this reaction in spacecraft. We probably use it in other places too. We use it in spacecraft because this lithium hydroxide absorbs carbon dioxide really well. So they make the lithium hydroxide in canisters, and they actually use them on Space Shuttle and the space station and other spacecraft. They have these, it's like an air filter. The air flows through it, the cabin air, and it sucks out the carbon dioxide, and the carbon dioxide gets bound up into this, and so after the cartridge is basically full and it's completely reacted, you take it out, you throw it away, stick another cartridge in. So that's a little lesson in how we take carbon dioxide out of the air in a spacecraft or in a closed environment. But in this case, given this reaction, this is balanced. Our problem says if we react 0.15 moles of lithium hydroxide with 0.08 moles of carbon dioxide gas, CO2, which compound is the limiting reactant? And the second part is how many moles of lithium carbonate, Li2CO3, can be produced. So without doing any math, think through what this problem is saying. What it's saying is that we have a reaction here. We know the stoichiometric coefficients that yield the perfectly consumed stuff on the left, yielding everything on the right. And we're given the amounts of what we actually mix together on the left-hand side. We have 0.15 moles of this, 0.08 moles of that. The question is, which one is the limiting reactant? And that's exactly what we talked about with the eggs and the cupcakes, right? We don't know, because this is 2 moles of this and 1 mole of this, it's difficult to look at what we're actually reacting. 0.15 moles of one, 0.08 moles of the other. It's difficult to look at those ratios and figure out which one's actually going to run out first, because our ratio in the reaction is 2 to 1, but our problem doesn't give us anything like that. It's 0.15, 0.08. So we need to basically figure out which one of these is going to run out first, and that's going to be our limiting reactant. And the second part says how many moles of this product, lithium carbonate, Li2CO3, how many moles of that's going to be produced? Well, that answer is going to be entirely dependent upon which one of these runs out first. I mean, think back to the cupcake example, right? You have the powder and you have, eggs, let's say. Well, depending on which one you run out of first is going to determine how many cupcakes you actually make in the end. Because the reaction is going to march along, proceed. Everything's going to be combining eggs and powder, eggs and powder, eggs and powder. Another cupcake comes out, another cupcake comes out. Whichever one I run out of first is going to dictate how many cupcakes I actually have in the end. Whichever one of these I run out of first is going to dictate how many moles of product I get. Now, if you look back, this is sort of an aside, if you look back to the problems we were doing in the last few sections with stoichiometry when I introduced it, those problems were worded carefully, you see, because I was always saying stuff like, you react this in an excess amount of carbon dioxide, how much of this is produced? So we got around this limiting reactant business before because I never really told you, I never really gave you 2 amounts here and said how much product was produced. It was worded in a careful way. We said, well, we have excess over here, or it was worded in some other fashion if you go back and look at those problems where you really didn't have to worry about limiting reactants. But in real life, when you mix 2 different amounts of something together, one of them will run out first, and that's going to determine how much of the product you get. So the way you do this is the same for every problem. What you need to do is do 2 different calculations, and this is just the way to do it, folks. What you do is, the first calculation is you assume lithium hydroxide is the limiting reactant. Once you assume that, you calculate how much product you will make, and you use the regular stoichiometry that we learned to do that. Next calculation is you assume this is actually the limiting reactant, and you use that information to calculate how much product you get. So you assume in turn that both of your reactants are the limiting reactant. You do a calculation to figure out how much moles of product you get in the answer using both of those assumptions. And then whichever one of those produces the least amount of product is the answer. That's going to be the one that really is the limiting reactant, because that will be the one that runs out first if he produces the fewest product. So that's really the logical way that we do all these problems. So that's what we're going to demonstrate here. And this is exactly how I'd write it down in my paper, by the way. I'd write the chemical reaction out, and I would literally write what I'm doing right now. I would write this: assume that lithium hydroxide is the limiting reactant. And you don't have to write limiting reactant all the time, just put LR. So if you make that assumption, then you just use stoichiometry all the way. Now look, it says if we react 0.15 moles of lithium hydroxide, so we'll just write that down, 0.15 moles of lithium hydroxide, right? This is what we start with in this assumption that we're making, that it is the limiting reactant. We want to find out if this guy is our limiting reactant and this is how much we start with, how much product are we going to get, right? Because this is the one we're interested in. It says how much of this can be produced. So we do the molar ratio, 2 moles of this to 1 mole of this. So we say 2 moles of lithium hydroxide for every 1 mole of lithium carbonate, Li2CO3, right? And of course, the reason we arranged it like this instead of upside down is because we're canceling moles of this with moles of this. So what we have left is moles of our product. So when you actually do this calculation, when you take 0.15 times 1 divided by 2, what you're going to get is 0.075 moles of Li2CO3 and produced. All right, so what we're saying is, basically we're pretending in this particular scenario that we start with 0.15 moles of this. We don't even care about the carbon dioxide. We're just going to, for this assumption, we're going to assume that we have a ton of carbon dioxide in the chamber. We have infinite excess amount of carbon dioxide. And if that's the case, assuming we start with this, how much product will we get? And we've calculated that. Now let's go the other direction and let's assume that the carbon dioxide is the limiting reactant. And let's see how it compares. Now, in our problem, we said we started with 0.08. 0.08 moles of carbon dioxide. And again, in this case, let's pretend this is the limiting reactant. So we have tons of lithium hydroxide laying around. We don't even care how much because we have tons of it. So let's see how much product we're going to have. The molar ratio is 1 mole of this to 1 mole of this. So let's calculate. We have in the reaction, 1 mole of CO2 for every 1 mole of Li2CO3. And of course, we arrange it the way that I did here for the same reason, so I could cancel moles with moles. And what I do is I say 0.08 times 1 divided by 1 is going to give me 0.08 moles of Li2CO3 produced. And all you do is you compare these two different cases that you put on the board. Basically what you figured out is that if this really is the limiting reactant, and I react this much of it with a ton of excess CO2, I'm going to only produce 0.075 moles of the product. And if I do it the other way, assuming that this is the limiting reactant with tons of the other stuff present, I'm going to produce 0.08. You choose the amount of the product that's less. That's going to be when the reaction truly stops. And think about the eggs in the cupcakes. I don't know how much powder I have compared to how many eggs. I need to start mixing things to figure out when I'm going to basically continue combining everything. Whatever I run out of first basically is going to dictate how many cupcakes I get at the end. And so if I do two calculations to figure out, well, with this many eggs, how many cupcakes will I get? Okay, I get that number. And then I do another calculation. With this much powder, how many cupcakes am I going to get? And then I look at the answers and I say, well, I choose the number that's smaller because that's really going to be when the reaction stops. Basically, we mix these things together and everything starts combining in the proper proportion to produce the product, right? Eventually, we're going to run out of one of these guys. The way that we figure out which one is the one we run out of first is to figure out which one yields the smallest amount of product. Because when we run out of that, when we stop producing product, that's when the reaction stops, and that's how we figure out which one's the limiting reactant. So, by looking at this, we figure out, because this one is actually smaller than this one, we figure out that, as our conclusion, that lithium hydroxide is the limiting reactant. That's thing number one that we figure out. And thing number two, the second part is how many moles of lithium carbonate can be produced. We figured out that 0.075 moles of lithium Li2CO3 is produced. And this really is the way you do all of these limiting reactant problems. You do two calculations, figure out how much product is going to be produced in all of the different cases, and then from that you determine which one is the limiting reactant by choosing the smallest number.